Good afternoon, everyone. Hope everyone is well. I'm just going to give it one more minute or so, or 30 seconds, 1 minute past the hour, just allow a few more to join, and then we'll get going. Okay, let's make a start. As I say, welcome along to this webinar. Thank you very much for taking your time out of your day to join us. My name is James Blair. I'm an account manager here in the software division at IC Blue. For those that aren't aware of IC Blue, let me just take a quick couple of slides just by way of introduction before handing on to the main event. Sure why. Here we go. Sorry about that. So yeah, IC Blue was formed back in 2003 to address a distinct gap in the electronic component market. It sits in the middle ground between direct manufacturer supply and mainline distribution, offering accountable procurement services tailored to your organization's specific needs. So if you've got any component shortages, any component needs, please do not hesitate to contact us. With regards to software, so in February 2016, IC Blue was appointed the exclusive UK distributor for Mentor Graphics EDA solutions. In 2018, with the acquisition of Mentor Graphics by Siemens Digital Software Industries, IC Blue became a Siemens solution partner for electronic and electrical design tools. Then in 2019, we formed a partnership with Downstream Technologies. They're a US-based company to be a solutions partner for them as well. They focus primarily on design for manufacturing tools. Below on the screen there, you can just see a few facts about the business, but more important there is the quality aspect. And the business is rightfully proud of those. We retain a number of quality aspects that's been in place for a number of years, and are repeated and renewed year on year, which is great. So we're headquartered in Leeds. The top photo is of headquarters in Leeds. New logistics hub with the 10,000 square facility, which we've been using since December 2020, which includes lab condition inspection and storage. We have a number of offices around Europe to cover multinational businesses. So as I said, we are an expert partner for Siemens. So obviously Siemens have a huge range of software. We cover a reasonably small proportion of that. On the left, with PCB design systems, we cover PCB design and analysis. So we have Expedition, which is the Siemens flagship PCB design tool for schematic entry and layout. Below that, there is Pads Professional, which is aimed at small to medium enterprises, but it's a very, very capable product within its own right. And on the simulation side, we've got Hyperlinks, where we're going to focus today in a short while. Valor is a industry standard design for manufacturer product. And below that, there is DFM solutions to add to Pads Professional, as well as an online solution called PCB Flow, where there are subscription options available to get your design ready for manufacture. On the right-hand side there, on mechanical analysis, we've got several different flavors of a tool called Flowtherm, which incorporates a full CFD solver. So for any thermal aspects, either the board level or within an enclosure, on the mechanical side as well, integrates with mechanical tools, then you can take into account airflow and so on to make sure your design's not going to overheat. In the middle, we've got some products for electrical and harness design, capital and capital essentials. So these tools are primarily aimed at aerospace and automotive, although it does cover a number of different markets as well. But yeah, that focus really on the increasing complexity of wiring and certainly modern electric vehicles, for example, and Formula One vehicles, cars, where obviously size and weight are paramount there. So a couple of solutions there. On downstream, so again, these focus primarily on design for manufacture. So we've got CAM 350, which is a very well respected tool in the industry. And if your business needs a lot of documentation, so for example, in the medical industry, then Blueprint is the tool for that as well, which can offer significant enhancements to document your designs and manufacturing ability there. So, as I said, very quick sort of introduction to IC Blue. As I say, primarily focus on the software business, which is where I reside, but obviously on the component side as well. Do not hesitate to contact us. The coordinates are down there in terms of telephone number, email address, and website. Okay, that was all from my side. Before I hand over to Steve, let me say if you have any questions during Steve's presentation, please enter those in the question section. There should be a question section on your sidebar. Please enter them in there, and we will endeavour to answer them at the end of the presentation, time permitting. Of course, if we don't get round to them, we can of course answer those individually at a later date. With that, let me hand over to Steve, who will take you through the presentation, the main presentation for this afternoon. Perfect. All right, Steve, yeah, we can see your screen, so you're good to go.
Perfect. Thanks very much, James, and thanks to everybody who's joined. I can see there's at least a couple of people I know, so it's good to see those people. So my name's Steve Gascoigne. I'm an application engineer for Siemens EDA. Been working with pads and expedition and very specifically hyperlinks for a number of years now. I think it's 24 years this month, in fact, I think, or end of this month. We've already in these webinars looked at some of the other functionality within the analysis suites. Today, I just wanted to focus specifically on AC or decoupling analysis. Talk firstly, about what the challenges that we're trying to address, or specifically, what are the parameters that we want to try and extract to understand how good our decoupling scheme is. And this word, good or goodness, we'll use a bit, because some of this is somewhat subjective or at the discretion, absolutely the engineer, but accessing the information from the design prior to having a tool like hyperlinks has possibly been hard and may have relied on a lot of, in the past, on a lot of experimental physical designs, or even arguably over designing from application notes. I'll run through my presentation, which isn't very long, and none of it's particularly complex, and then we'll look at an example in hyperlinks itself. First of all, just to see the mechanics of how we would achieve our analysis and what we can extract, and I hope so that we can get a view on the ease of use of hyperlinks. And it's sometimes it's an overused term, and we have to be careful. Ease of use is slightly different as easy to use, in that we don't. There is quite a complex process going on in the background, but we want to make it very accessible. That's the key thing. For sure, I think any engineer now wants to have access to this kind of functionality, but doesn't want to have to spend hundreds of hours becoming an expert in extremely complex methodologies to get to the answers he wants. So hopefully that will show as well when we come to the demonstration. But I'll explain a little bit more when we get to that. So I imagine I don't need to run through this in enormous detail. I think we all understand why we have a need for AC or decoupling analysis. We want to primarily understand the number of capacitors I need to perform my decoupling sufficiently on my printed circuit board. And depending on your product, typically, this is something that's driven by possibly volume or cost and volume, or in some cases, the intended application of the product. There are some products, space products, for example, where for sure it's going to be very difficult to get it back and modify it, and having it primarily right in the first place is critical. Also, mixed in with that understanding, how many caps and how many caps or capacity each value I want, I need to know where I'm going to place these capacitors to be effective. This absolutely comes into play where I may have implemented multiple decoupling schemes from different IC vendors. I've got different technology on my board, and I want to understand if fundamentally I have redundancy, or whether I can take advantage of co-location of capacitors. Also, depending on the structure of my board, which is probably driven by the complexity of the board, I need to very clearly look at how effective the capacitors are in their mounting. And I'm going to talk a little bit about how we calculate or how we can extract even simple information about that to help me to drive a more efficient board. I may be exploring other techniques. I may be looking at new technologies like embedded capacitance, and I will mention, when we look at what we can extract from the design, how we do include the embedded capacitance of the board, and it may be I want to move to use embedded capacitance. I may want to either look at dielectric material or possibly even look at embedding capacitors themselves within the board. And for sure, we can analyze that. Whether or not your PCB design tool or your PCB fabrication technology supports that may be a completely different discussion. And then finally, once I have a decoupling scheme, looking at it, in the frequency domain, and that's what I'm looking at in this little snapshot I've got here at the lower right hand of the corner, is one methodology for validating it. Another would be to look how noise propagates around my power distribution network. And again, I'll demonstrate that. We have a very straightforward interface whereby I can inject noise and look how my entire decoupling scheme handles it. And of course, just in case it's not obvious, the advantage of analysis and simulation is within my model, I can make modification and do what if analysis, try changes well before I commit to the physical realization of my board. And I'm pretty sure I've said this before when we've done these kinds of presentations. The earlier I can make a decision, for sure, the more options I have. Also, the earlier I can make a decision, it's likely any change I make will be a cheaper solution. Conversely, if you like, the later I leave a design change, the more expensive that change will become, even to the point where possibly I can't contemplate a change, even though I know it's good, because it's way too late in the design cycle. It's going to be too complex, too expensive to implement that change. And fundamentally, this is why we end up with revisions of printed circuit boards. We don't see it so much now, but in the old days, we used to see a lot of boards, with cutting straps, and fundamentally that would be the reason. Thinking to the functional requirement, putting cost and processes aside, the functional requirement is, of course, that we need to deliver AC current across all frequencies at the switching or contributors to the switching frequency of our devices. To achieve this, we want our PDN, our power delivery network, to have a low impedance. If we have a high impedance or spikes of high impedance at frequency, we'll have inadequate current delivery, and this will essentially lead to voltage ripple. If the voltage ripple, is consumed by the devices or becomes consumed by the devices, it's going to lead to other problems, and is for sure a key contributor to signal integrity problems, leading us to closed diagrams, bit errors, timing violations, and many other issues. Plus, if my decoupling is poor, it will allow noise to propagate throughout the board. If it's on the plane, it will propagate throughout the board. If it's not suppressed, anything that's plugged in the board will get the noise propagated to it as well. And okay, we're not specifically looking at common mode EMC today, but a contributory factor again would be poor decoupling. So we'll think about very briefly, what can we do in hyperlinks? And I know some of the people, because I can see the names on the call, are familiar with hyperlinks. And I would arguably say some of the people on the call are advanced users of hyperlinks. But within this analysis environment, we can effectively do two kinds of analysis. And this applies to both power integrity, AC or DC, and signal integrity, whatever form your digital interconnect is. But I can do, firstly, post-layout analysis. And this is what we're looking at here. Post-layout analysis just really refers to the stage in the design cycle where I actually have CAD board data available. The board doesn't have to be finished. It could be partially finished. It may only have critical board areas of the board complete. I can for sure go on and analyze those. So I'll read my board data into BoardSim as the environment, just if you're not familiar with it. I'll probably say this multiple times. I can read PCB data from any PCB design tool into hyperlinks. We're not limited to Siemens PCB design tools. We can come from Zuka, we can come from Cadence, we can come from Altium, and anything else very specifically that could make an ODB++ file for us, because we read that format natively. Then we'd analyze the impedance profile of our PDN, our power distribution network. I can make some small changes in here, because obviously really at post layout, I'm quite a way into the design cycle. So there's some small changes I can consider directly in here, probably fundamentally revolving around the modeling of the devices themselves. And I'll come back to that later. And the structure of the printed circuit board. I could influence its stack up. And again, that's another complete topic in itself, the definition of stack ups, material selection, and of course, the correct modeling of those materials into not only this analysis environment, but arguably any analysis environment. If I want to make a more fundamental change, we'll see on the next slide, I have the ability to go into more of a kind of a Lego mode or a drafting mode, where I could make changes to the copper. I'm not making changes to the board itself, the board layout itself, because I'm looking at a snapshot, but I can experiment with my thoughts, my ideas, before I commit those to the PCB, because possibly having the PCB modified, involves a third party, or it for sure involves, some time to do that. And then finally, I can actually do a noise analysis, so I can visualize the decoupling at work. So look at it in the transient mode, the voltage mode. I'm going to demonstrate that directly. I've already mentioned this LineSim tool, exporting something to LineSim. LineSim is our pre-layout environment. So this I can begin to use even at the conceptual stage if I want. Fundamentally, when I'm trying to probably refine my ideas of how I'm going to perform, in this case, decoupling, although LineSim also supports DC drop and also supports signal integrity. It allows me to do a complete what-if analysis, because I have full control of the objects, placement of devices, mounting devices, the modeling of the devices again, and of course, again, things like the stack up build for my proposed printed circuit board. As I mentioned, when I was looking at post layout, I can also use this environment to experiment with changes from the layout. I basically extract just the plain information that I want to work on. And in here, I have some rudimentary drafting tools so that I can experiment with, for example, adding or removing copper, moving devices, adding more devices. If planes are stitched together with stitching vias, I could add or remove stitching vias, obviously, because that influences how noise will propagate and the EM model of the plane itself. And as well as doing the frequency analysis or frequency domain analysis, again, looking at the bottom there, we have a nice picture where I'm doing transient noise analysis, injecting current into the plane and seeing how the resultant voltage propagates across the plane. And the plane behaves as what we call a transmission plane, a little bit like a transmission line. If the noise that's propagating hits an impedance discontinuity, it gets reflected, and the noise moves around the plane, not only influenced by its shape, but influenced by its decoupling or its capacitance, however that becomes formed. This, of course, is or the line sim environment is, of course, completely independent. Think of this as, like a this is my scratch pad for ideas, where I'm working, as I said, possibly before I've even placed a single device within my schematic for my PCB. Thinking of the actual capacitors we're modeling, and we are going to model all capacitors either within my line sim proposal or within the board itself. Hyperlinks is able to identify what a device is by its reference designator. So effectively, I'll become prompted with a list of capacitors which I want to model. I'll show you exactly how that works, and there are options for that. We could call them, I don't like the word accuracy. There are options for the modeling of the capacitor which take into account different physical phenomena. There's a simplistic mode which may miss some of the structure of the device, moving forward to a more comprehensive mode, which I get a model from a vendor, which takes into account not only the structure but the physical aspects of the device. The device we're looking at, of course, is going to be our bypass caps and of course our decoupling caps. We include bypasses because they may serve both purposes. In fact, and for sure, I want it to be part of my entire frequency domain model of my plane. So thinking to modeling capacitor, it isn't just about the capacitance. If it was just about the capacitance, we could probably do some of this analysis directly just inside, I don't know, an Excel spreadsheet or something. And there may well be simplistic tools available which will allow you to load capacitances into a graph and plot their impedance and look at their series and parallel resonance points if you've got multiple values. But the reality is that a device, just the device itself, comes with some parasitics. So on top of the capacitance of the actual, the value of the capacitor itself, it will have some capacitance through its physical location to the transmission plane, the plane on your actual design, obviously, depending whether it's mounted top or bottom and the position of the planes within the board. It has a series self-resistance. This is can be determined or is documented, can be measured, and is documented typically by the vendor, as well as its mounting resistance. We can talk about mounting quite a bit. And the same is true with its series inductance. It has a self-inductance, and ESL and ESR, as I said, are a function of the package of the device itself. Plus, it has an inductance of the mounting structure, parasitic inductance. So what we can extract from this, if you like, is in addition to those inherent parasitics, the capacitor mounting is also going to greatly affect its performance. And we could sort of, if you like, check this off as perhaps a task I would want to perform as part of my decoupling analysis. The first thing I'm going to do is look at the characteristics of the mounting to determine whether it's going to affect how well my capacitor behaves as a decoupling device. And just at these pictures, okay, I've taken these from the mounting scheme editor. It sort of helps me share with you, visually. I can, when I'm doing experiments, when I'm working in what, as we mentioned, this licensing tool, I can work on things like the mounting. I can just purely accept the capacitors as they are, and then think about how will their mounting affect their performance as a decoupler. And it's a very straightforward graphical environment. What you're looking at here is pretty much what you see. I can attach the pins to vias. Obviously, here we're looking at well, these could be surface mount devices because the vias absolutely could be within the pads, or I could be looking at axial or radial devices with tracking to the first vias and how they connect to the planes. And of course, on top of that, I may consider what happens when I've got capacitor pins sharing vias, or capacitor pins sharing the tracks to the vias, because that would absolutely affect ESR and ESL, which we knew were key parasitics. If we looked at that in the frequency domain, we can see the equivalent circuit, this L, R, and C circuit, gives us the real behavior of the capacitor. And when we're observing the frequency response of our entire PDN, effectively, we're looking at across the frequency domain, multiple capacitors. We want to understand, what forms the shape of this plot for us. So we know that for sure the actual capacitance of the device is going to dominate at lower frequencies. And here I've plotted what I'd imagine, is a single device mounted. Obviously, that changes with multiple devices, and especially if those capacitive sim values have different mounting characteristics, I'm going to get a different V shape. We know that inductance dominates at the higher frequencies, but the real capacitors are low impedance, but it's only in a fairly narrow range. A single frequency for a value. This is why we use multiple values of capacitors to give us a low impedance across a much wider frequency range. And we can relate this impedance to the equivalent circuit. So we can see that the resonance frequency is 1/2 pi the square LC. We know where L and C have come from, thinking back a couple of slides. And then the impedance of the capacitor at resonance is its resistance. Remember, L, C, and R here are both apparent, the inherent, and also the parasitics of those, which includes the mounting. I can't stress enough that not taking into account the mounting, either pre-layout with proposals or post-layout with the actual tracking. If I don't take that into account in the analysis, I'm going to mislead myself enormously. So, looking more closely, we see that the dominant effects of the capacitor's behavior are going to be, for the L, mainly the mounting, and the inductance of the mounting is going to be determined by the sheet inductance of basically the track or the copper connecting it to the via, plus the inductance within the via connection itself. Sheet inductance in the traces is a function of aspect ratio. Long, thin traces have high inductance, fat, short traces have low inductance. And that's something we could, so arguably you could visually verify that, but it's going to be much, much quicker and more accurate to extract that and put it to a table. For R, it's going to be mainly the ESR of the device, which we know is a function of the physical structure of the device, and is an extraction from, or that data is extracted from the data sheet. If I didn't have that available, I can early on, and possibly up to sufficient, actually approximate that from the package style of the device, because for sure it's going to be similar across same package styles of devices. And of course, C is dominated by the capacitance of the device itself. And for sure, like any kind of analysis, it's easy to get the value of a capacitor and put it into my model. Just for reference, and I'll try not to bang on this drum too much. If I was coming from a Siemens EDA tool, we can absolutely read over the things like the value information of the devices directly. If you've incorporated the value within, depends how much you neutralize your export from other tools, that will be read in through ODB++. But there are mechanisms whereby essentially we can read in the capacitance values. It's a bulk operation. We're not expecting you to have to necessarily visit every device, somehow edit its properties just to get the capacitance in. We have mechanisms for doing that, and I'll show you how that works. I did mention embedded capacitance. Just thinking very specifically to the structure of the printed circuit board. Looking to the picture on the right, if I look at the top there, I've got my VCC and ground plane. If I've got two big flat bits of copper with a dielectric in between them, which is the structure of the printed circuit board, I have a capacitor. So there is some natural capacitance to be will be generated by the plane shape itself, and it is the shape. Now, pre-layout, I may only have an idea of the rough size of my board or the size of the planes, Obviously, post layout, when I've got the true plane data, it also includes things like all the via voids, all the nibbles, all the things which influence the exact shape of the copper. And absolutely, we're going to use that to generate the C model, the capacitance model for the plane itself. As it says here, just in this comment, this is only effective, particularly at higher frequencies, because it's a very low value. We mention it here because, again, it's another, how you call it, it's another blade in my Swiss Army knife. When I'm interrogating the frequency plot, I can determine, okay, at the high end, I know I'm looking at the capacitance generated by the plane. As the plot goes off lower left to upper right at the high end of my frequency. And again, this is just underscoring that. Of course, as we know, fundamentally, the energy in my PDN doesn't travel in the copper itself. It's traveling in the void between the copper, which I've just said is a capacitance. Therefore, any other capacitance connected to it must also be a mechanism for propagating that energy. And I think it said on the first slide, decoupling capacitors are effectively little pots of energy that, or pots that store energy to be delivered to my ICs. I want large capacitors, a small number of large capacitors around a board to be essentially, big pots of energy that can deliver current to the board. As I get nearer to the devices, I want devices which can react more quickly, so at a higher frequency. So there'll be smaller capacitors, but many more of them much nearer the power pins. Sorry. And we'll talk about, okay, there is a slight differentiation in analysis I want to do then. As well as taking into account the effects of these devices, it sounds like I need to take into account the position in relation to my ICs as well, if that forms part of the equation. And we'll talk about these analysis methods, because I think already I know we've kind of touched on three, mounting effectiveness, overall capacitive effectiveness, or the impedance of the overall plane, and then the impedance of the plane taking into account capacitor position. So therefore, the impedance of the plane with respect to individual power pins looking back to the VRM, or the voltage delivery source. And to underscore that, that's pretty much what I've said. It's the energy is provided and stored in this hierarchy. The further away from the IC supply pins, the more energy will be available. The nearer to the IC pins, the less absolute energy is available. But there are many, many more of these devices absolutely near the pins. So if it gets distributed, almost like a family tree, a tree structure. And this is what I'm effectively want to validate at some point, that I have accounted for this correctly. When we're looking at the decoupling, we do want to consider the complete current flow. So I did mention, inductances, or parasitic inductances in mounting of the tracking, parasitic inductances in capacitors. I've briefly mentioned vias. Vias for sure have a parasitic inductance. We want to account for this. In some cases, perhaps just estimating it is sufficient so that we can drive the placement of our planes and the placement of our capacitors. We can see, I think, in this picture, if capacitors are mounted on, they are mounted on the edge of the board typically. Some people may have embedded caps, but if they're mounted on the edge of the board, the distance from that side of the board to wherever the plane exists will form an inductance loop. And for sure, there's an inductance parasitic formed by the difference in the length of the vias between the two planes I'm trying to decouple. And that there is always going to be a difference, because the planes are going to be probably on different layers, so the vias will be different lengths. This drives possibly what you've seen as a rule of thumb. You should always have planes as near as together as possible within the stack up, and as thin as possible dielectric in between them. For this very reason, it generates a low parasitic inductance connection for decouplers. Also, it will equally arguably generate more capacitance in the plane itself. As it shows here, the further away from the green is a device, the grey device being a capacitor, and the further away from the device, the more the inductance of that connection. within the plane as well. Now, some of these methods, you could do by, and you call it, first order calculations, or through approximations, measurements, applying rules of thumb, applying constraints to your device. But in many cases, it becomes quite a tedious task to do this, especially if you've got hundreds of devices, especially if you want to make trade-off decisions. Doing something manually analytical is okay if you're looking in one direction with very few considerations. It becomes complex when you're trying to make trade-offs with other connected scenarios. But using Hyperlink's PI, we can take account of all this using our transmission plane modeling. Now, without getting into the detail here, there are some options again available on how I model the transmission plane, or the mechanism I use in the background to generate that model, which will be an impedance, typically an impedance Z parameter model, because we have very complex coupled geometries. Within either the line sim or board sim, fundamentally, whatever geometry I presented will be automatically decomposed and a model made directly, suitably for me. I mentioned this already. We've thought about we're talking about looking at impedance. So the looking in impedance can be thought of as a Z in series with the incoming power distribution network current, because as we said, we want a low impedance delivery path between the voltage source, the VRM. And here I'll talk a little bit, I may mention the term VRM a couple of times, voltage regulator module. It may be on your design, it's not actually a voltage regulator module, it's a pin with a voltage coming in. Well, that's sufficient if I'm just, for modeling that board. Fundamentally, I'm going to present the tool with a voltage at a location. Okay, that voltage source, has an input impedance, but it's the board I'm fundamentally interested in, the interconnect on the board. Since all the IC is attached to this transmission plane, and it can only tolerate some small voltage ripple, as I said, and fundamentally that's what we're trying to control is ripple. We can immediately calculate that the impedance of the plane is the voltage, acceptable noise voltage, divided by the maximum current we expect to see. And in most cases, of course, we're going to go somewhere near worst case. I know that devices have transient current consumption, but typically I want to account for the worst case scenario. But I can control this within my analysis. We could apply some numbers to that. One of the things I perhaps want to think about first is what does this number typically look like? So if I needed 20 amps peak-to-peak switching current and some clock cycles, it'd probably give me something like a 10 amp max current. And if I'm going to say I can only tolerate 5% VCC ripple, we can quickly calculate that there's something. The impedance of the plane is going to look something like 9 milliohms. We're always going to be in the milliohm region for this. Fundamentally, in this calculation, I think we can see the impedance allowable would increase if we were to accept more ripple. I'm not saying we should design, accept a poor decoupling scheme by saying we'll accept more ripple, but we can see that that absolutely is the connection. As we mentioned earlier, poor decoupling will give me more ripple. Simple as that. So here's a sort of an equivalent circuit of that. Looking in from the left-hand side, I have my Z, my impedance. What I effectively see is all the capacitors connected in parallel across that, including their parasitics. This methodology we're looking at here, we could consider to be called a lumped impedance model. At this point, it's as if I have all the capacitors in the same place. And as we can see on the far right-hand side, I'm going to include the capacitance of the plane as well. This would absolutely give me a first pass look at how good my decoupling scheme is. So what we actually get is this Z is actually called a Z parameter. We plot this. Obviously, it's implied by impedance. It's going to look at the value of the impedance over a frequency range. The range of the frequency we look at is going to be obviously lower than the propagation frequencies of your digital signals which are in the devices, because the switching frequency of the device, the power switching frequency, is much lower. And also it's going to be walled at both ends. We're never going to go typically below 10 megahertz. Once I go into extremely low impedance of the plane, that area of the plane is going to be dominated by the impedance of the VRM, which I can't control. We've already said it is either a VRM I've modeled or it's just a power supply coming in. As I go up to the higher end of the frequency, once I go beyond the capacitance of the plane, on a real board, if I was to measure the impedance of that plane, what I would see is an area dominated by the input impedance of the devices, the power pins on the devices themselves. And again, I can't fundamentally control that. We'll imagine the devices are pre-specified. So I'm going to limit my area of discovery, my area of evaluation, to the area dominated or which contains the capacitors themselves. But very specifically taking into account not just the different values, which obviously give me the different V points. If you like, we said the frequency is determined by the capacitance, but I also want to take into account the effects of their mounting, and at some point probably the effects of their location. And I'll come back to that. So if I didn't have the effects of the mounting, if I was to model an ideal capacitor, then I would see a much more different plot. And this is the reason why I want to take this evaluation from a purely theoretical analysis to a board level analysis with the extraction of the parasitics. Everything includes the parasitics of the devices, the mounting, directly within one environment, so I see the combination of those, and it allows me to make trade-offs based around those. Because fundamentally, I probably have two choices: add or remove capacitors, or change where and how the capacitors are fixed to the board. And those are the things I can control. I must have the characteristics which are representative of that. So I already said this, but just as a reminder, because when we come to set up the model, we want to see how this is done. The L, we mentioned the self-inductance of the device. I must have to model that. It's a function of the packaging, the physical form of the device itself. Obtainable probably as a value from the data sheet. The same is true of ESR. Also, I can approximate based on package size. There is a way I can include a more comprehensive capacitor model. In many cases, capacitors which are used specifically for decoupling, part of their data pack, if you like, may well be an S parameter model of the capacitor. This is obviously taken from measurement and absolutely takes into account all the parasitics of the device, including its physical structure, how the capacitance is realized within the device itself. If it's been measured in place on a board, it may also take into account the true parasitics of the mounting of the physical structure of the capacitor, the internal structure of the capacitor with relation to the printed circuit board. However, and I know some of you use this tool already, if I don't have this available and earlier passes, I can implement values which are absolutely acceptable to represent this, up until the point, perhaps as I get further into the more of like the validation, the compliance analysis, where I'd want to implement these. Now, I use the word carefully, more detailed models to ensure that I know my plots are more representative, or have more accuracy or correlation to real world. Accuracy is always a bad word, I feel, because the simulation is always as accurate as the information you present to it. And if I can present more detail, I see that detail in the outcome as well. Just as a reference, really, I'll leave this in now because I'll share this presentation afterwards. There's nothing in it that isn't, I won't say is not common knowledge. The ESR, as I said, is generated from a data sheet. C is of course the nominal value. ESL can be measured by the vendor. Again, we can implement it as a bulk value within the model, or if the capacity is presented to us with a more comprehensive frequency-based model, it's absolutely 100% within that frequency-based model. Thinking to the effects of mounting, and I've sort of touched on this a little bit. I've taken a snapshot here from something in the Xilinx data sheets, just because they had some nice pictures, to be honest. And it's another source, not just something that we've produced. Again, thinking about the inductance of the mounting, I already said this, long thin tracers are going to give me a poor ESL for the mounting outside the device. Of course, I know it's kind of caught my eyes now on this picture. When I have board data or pre-layout data, I can also include the parasitics of the mounting pad. In fact, in many cases, that may form a key parasitic, which is directly derived from the package style I've used, because for sure the mounting pad is a direct function, or the size of it is a function of the size of the device connected to it. As we go left to right here, we can see making the traces shorter and fatter. I'd say its aspect ratio really is going to be decrease the ESL of the mounting traces. Moving to the third from the left, moving the vias close together, so putting the vias to the side of the device, thinking to the cross-sectional view I had before, moving the capacitors nearer together will reduce the inductance loop inside the board itself, irrespective of how thick the board is. Now the devices are close together, I've decreased the area of that loop, so I've decreased the inductance. And to do it further, I could double it up. Obviously, it's going to be the reciprocal of that. In that case, it's going to be smaller than either of the two added together. You probably see this. You've probably seen this is not something Siemens specific. This is probably third day in the electronics class. How to mount a capacitor better. But for sure, we want to be analysing this. My board may not always present me with the opportunity to do the ideal thing. So I want to have the, knowing these rules, I probably want to have the opportunity just to identify this in the first place. Arguably, this, I don't even need to quantify inductance. A visual inspection. In fact, that's what the first order check in Hyperlinks is a kind of visual inspection for how well the cap is mounted. One of the things will be basically how far from the cap pin to the via, how thick is the trace, and how many vias are there, and how close are the two vias for a given device. This in cross section just basically tells the same story. So, mounting vias as short as possible. I already said it grows with this is board thickness, of course, we're thinking of now. Well, not board thickness, position of the planes within the boards. I think it's common to have planes, just inside the structure of the board, especially in a high-speed design. So I get nice traces on the outside of the board as well as on the inside of the board. But for sure, if I've got power delivery, I can put them to the outer pairs rather than the inner pairs of the board. It's ideal. The buried capacitance I already mentioned is a part of this decoupling structure. So having those two, the voltage in its reference plane as close together as possible. I think down 4 mil or something, or 4 thou would be something like the minimum. But I think also perhaps thinking about dielectric material that runs between them. It may or may not be an option for you. It likely introduces cost, which may or may not be a deep consideration for your specific product. And as we saw in the overhead view, having the barrels as close together as each other, because the opposing current acts differentially, and the H field will cancel itself each other out, so it reduces this parasitic inductance in the vias themselves. Already looked at this same picture. So if I did a lumped analysis, I could effectively connect all these together in a similar location and plot a Z parameter, which would take into account all the things we've spoken about, and give me an indication very quickly of how, looking broadly for the entire plane across the frequency domain, of how well I've decoupled my device. And I can compare that against a threshold of a known low impedance I want to achieve. So the advantage of this, what we call lumped analysis, is it does run very quickly. Since the circuit only needs to be AC swept, effectively there is no there's no spreading impedance of the interconnect, the physical distance interconnect between the ICs, power pins, the capacitors, and other capacitors, because they're all fundamentally at the same location. We get this very quickly, and we get it when we say cheap in time. It's easy to realize. The next stage up from this, I don't know if the picture shows it, yes it does, will be to insert a further model. And this multi-pin model that we'd insert would be the distribution of the capacitors. So the physical relationship between the capacitors, other capacitors, the VRM, capacitors, and the power pins. So my T-plane distribution model effectively is this map of the printed circuit board, taking into account the spreading impedance of the plane itself. This allows me then to absolutely determine how effective individual capacitors are with respect to individual power pins, or rather from each individual power pin, which are the distributed observation ports, as we call them. I could look how good is uniquely the impedance for that pin, looking physically back towards the VRM, taking everything into account, including things like if there is switch noise, how it propagates across the board, and how using the spreading impedance, what happens when I hit the edge of copper, whether the edge of the copper is the edge of the actual board or just voids or holes within the copper. And this will be analogous to if I could, put an analyzer on the power pin and measure the frequency response looking back towards the VRM. So something which you would never realistically perform on a physical printed circuit board. It is possible. We have done it. We've done it for correlation reasons, but for sure, in analysis, runs sufficiently quickly that I can make decisions within a daytime to determine whether my decoupling scheme is good. There is one level of automation we can sit above this. I've not discussed it here, and in the interest of time, I won't cover it entirely. But it would be possible to run some advanced algorithmic analysis, and I do have customers doing this very successfully, whereby I can say, well, I know what my goal is. Could the tool optimize basically the values of the capacitors based on my positions to give me the impedance I want, either with minimal capacitors or with minimal different values of capacitors? I say there's automation to perform that, and also I can do that manually. So very quickly, because I realize we've only got a few minutes, I wanted to make the demonstration as quick as possible. I want to just quickly drop into two examples and look at, or into my example, and look at extracting the three things we've spoken about, so we can see how quickly we can do it. I can extract mounting characteristics, I can extract a lumped analysis, I can extract a distributed analysis. So just jump over to hyperlinks itself. I know some people have seen this. In this example, I'm in the pre-layout version. I've actually created a representative printed circuit board myself in here. I've got some rudimentary drafting tools. I created a board outline. I have a stack up, of course. Remember, the parameters of the stack up are key to my decoupling. Effectively, I've got a 4-layer board with 2 power planes. In my example, let me say okay on that. We can see in yellow, I've got my power plane with a cutout and a void for no reason other than just to make it a more complex shape. For reference, if I was in board sim, I see the exact same detail. The difference will be, obviously, I've read in my actual board data, my copper data, my capacitor positions, at whatever stage the board's got to, partially complete or fully complete. In here, I've manually placed caps. I have a tool over here for placing capacitors. If I just hover on it, so I can put down decoupling caps. I've just placed a little array here of 9 and 1 by itself up here. Then I've imagined there's some power pins. You can see here I've put some power pins down on my design. Before we come to look at two things: distributed analysis, because I need to know about position, and plane noise. So let's just do the first analysis. The reason I'm just using a pre-layout here, I should also say, you saw I could make modifications here. I could extract an actual design back to this environment and play with adding capacitors, removing capacitors, adding stitching wires, changing the shape of the copper. in a very flexible environment before I commit those changes back to my PCB layout tool, where it may just take time. There's other guys involved, and it consumes time and money to get them to do the change. And probably there's other considerations. If I'm moving stuff about, I'd probably have to think about some other things as well. But I can experiment here. So in this case, let's look at the first thing I spoke about. I'm just going to invoke the decoupling wizard. Everything in hyperlinks nowadays is predominantly wizard driven. So the tool will ask me questions to get to the point where it can give me an output. So I'm going to do a new setup. I'm going to do my what we call quick analysis. Basically, look at how well the capacitors are mounted to the board. It's going to, because it's a visual check, I don't really even need to know which planes the caps are connected to. I just need to know their caps. So here we can see it's already identified. This is what we've called group 1. This is this cap C1 by itself. And I can, by clicking here, I can assign a model to them. For the decoupling, for the mounting analysis, I don't really need that, but I've already gone to the trouble of doing it. On a real board, with many caps, many different styles of caps, Hyperlinks automatically forms these groups. It looks at basically the part type associated with the device and says, well, if 2 caps have the same part type, they're probably the same cap. I can just do one model assignation for the group. Say next, and that's it. I just run the analysis. Comes back in 2 forms. I always get a textual report, but for everything now, I get a HTML aggregated report, which is, of course, I can share. Somebody else could look at this, even if they don't have access to hyperlinks. I have my simulation settings. I've got my results, and we can see my example, all my capacitors, the mounting quality is good. Now, obviously, I define the mounting quality here on a real device, on a real design, sorry, a full PCB. It's going to look at the actual tracking to figure out if it's good, marginal, or poor, and then tell you why it's arrived at that. It's either, if it's high inductance, it's either just typically to the traces or the vias. It's going to tell you which. Just for reference, if I double click on one of my cap models, you can see here was my mounting scheme. In fact, and as we saw in the PowerPoint, I have the opportunity to modify this is very simplistic. I've got some sort of axial devices here with vias associated to them, but I can make it surface mounts with vias in the pads or vias on tracks. It's my decision at that point. And of course, if whatever I've done in a PCB, that is absolutely extracted from the PCB layout. We take whatever devices you've realized. The next step we mentioned was the lumped analysis. I want to look at the capacitors in the frequency domain, taking into account the parasitics of their mounting, but I want it quickly. So I don't care about position. It's really like the caps are all shorted together at the same place, but include the parasitics and the plane capacitance. I do now need to choose a plane and its reference. I always have to have 2 values, 2 nets in here, if you like. On a full board, of course, I may see many, many more power rails. I need to choose a power rail and its reference. Again, because I've already done this for the previous step, I've modeled my capacitors. Notice here I can switch caps on and off, which may be something I consider groups of them. Or, of course, I can change the model, which effectively is like changing the device. I do have VRM assigned. I don't really need to know about where the VRM is at this point. As it happens, it's this U3 pin 1. But for sure, when I get to distributed analysis, I absolutely care where the VRM is. I can, for the purposes of the plot, calculate my preferred impedance, my desired impedance profile. So I can specify, we saw the current consumption, we saw the ripple and the voltage assigned. And from that, it just calculates a value of impedance for me. Nothing more than that. I could have typed it in here if I knew what value I wanted to achieve. There are some settings then. I'm going to go with the general settings. So I'm just going to jump through these because in the interest of time. But fundamentally, I hate the word accuracy, but they're settings, for the simulator in the background. And here is my frequency window. I'm going to do 1 megahertz up to 150 megahertz. Again, run that analysis. The output of this is going to be a plot. It's going to be a Z impedance plot. And there we are. If I move in the HTML report, here is my impedance plot. I had two different capacitor values, so no big surprise. I see two series resonance points for the capacitor values. Obviously, the shape of this has been determined, we know, by capacitance here and inductance here. And then I see parallel resonance points, obviously forming an adversion to those. And then over here, I know this piece of capacitance here is representative or is dominated by the capacitance of the plane itself. Just to confirm that, also I should have said it has also opened just a tool which allows me to look at the plot of that Z parameter. I'll just change the color, something that looks better. And that's what we saw in the report. If I leave that open, I could close this and I could go to the stack up. Let's do a simplistic change. If I change the thickness between the planes, now I realize that my overall PCB thickness is not super representative. I just want to go back and ensure that when I did that, it does influence the plot. So I can just run the analysis because I've already set it up. And there now, between the red and the yellow, we can see the difference. If I just get rid of the new report, we can see the difference formed by just changing the thickness of the trace. It didn't just change, remember, the capacitance of the planes, it would have changed the parasitic inductance of the vias because they got shorter as well, and the difference between them got less. So that's why we see a change at the capacitors as well as a change over here. So back to my final couple of things, because I realize we're just about to run over on time. And this is really just as an insight into what can I extract from this tool quite easily and quickly. Just put a plane back how it was. The other thing I spoke about was distributed analysis. So again, I'll go into my tool. I'm choosing distributed, choosing the same two planes I had before. Now as I move down, capacitors, I know I've modeled them. VRM, I know I've modeled. My impedance, I think we said was, I can type in now, we calculated 90. Now, which power pins do I want to observe on my board? There's U2 here, looking back to U3, and U1 looking to U3. So I just select those. I think it's finished, yep. And now, firstly, in the touchstone viewer, or the parameter viewer, I'm looking at the plot. Notice there is a subtle difference now. That's because I'm now seeing the effect of that void, or rather the difference in capacitance as we pass the void. And again, I see the same in the report as well. Last thing, because I realize we're pretty much out of time, and again, is to try and keep this as straightforward as possible. I mentioned that we can look in the frequency domain. It's absolutely a way to clarify my PDN structure with respect to any performance criteria of the individual devices. I can also look in the time or transient domain. So I have the ability, now I'll show how I do that. I go to my power pins, because remember we were imagining U3 is the VRM. I go to my power pin U1, and I say it has an AC model. So this is going to switch on to 1 amp. Remember I said that was our peak current in 0.15 nanoseconds. And I could also do the same with U2 as well. So I'll just enable that. And then when I go to my power scope, we call this, same tool we use for DC drop, start simulation. Noise was introduced to the power plane, and this is what the worst case noise will look like. And here obviously I'm looking at the plane in 3D. I can navigate this. I can look what the plane noise is at any point. There's no real surprise. Up at that top corner, if we look, I've got no decoupling capacitors compared to down here. I see a lot more noise because it can propagate more freely. The decoupling is pretty weak up there compared to this lower area. Again, if I want to experiment with a changing capacitors, changing the stack up, I'll do the same thing I did before, just because it's pretty straightforward. Change the thickness of the dielectric. That will change a lot of things, but will fundamentally increase the capacitance in this area at the top. I go back, resimulate. This simulation was running for, it's pseudo transient in that represents 10 nanoseconds of time whilst it was running. If I was to run this on a post layout, a real PCB, yes, there's a little trade-off. The more complex the shape, the structure, the little longer this simulation, the generation of this information does take. But here we can see the new plot. Initially, it looks similar. Here's the previous plot, but I can do a comparison, and now we can see, yeah, sort of as I expected. We did something where we thought we knew what the outcome would look like. We can see the noise has decreased in this area of the board where there were no decoupling capacitors, but I do have now more natural capacitance in that area of the plane. Cool. That's fundamentally what I plan to show, and as I kept it to this pre-layout environment, fundamentally just because the simulations run quicker because of this. This is a fairly simplistic geographical shape. The exact same functionality is available if I read in a post layout or a true layout design from any PCB design tool. Just as a reminder, we can see takeaways. Very quick to extract information about how well my caps are mounted. That could be my starting point. I just need to go back and look at that. The lumped impedance, which is a good test for how good, the goodness of my decoupling scheme. And then the final test now, which correlates directly to the real world, something you can measure in the real world, very difficult though, would be distributed analysis, i.e. from this power pin and this power pin having a unique impedance plot, observing from this point, looking back to the VRM, taking into account the shape of the copper, the capacitors, and the position of the capacitors. Obviously, some of them will have no marginal influence on that performance. In my simple example here. Cool. Gone over 10 minutes. I apologise for that. I always get carried away when I'm talking about these things. I'm just going to check. Were there any questions in the chat?
Well, Steve, yeah, excellent presentation as always. Thank you for that. Yes, there's a question in there. So it is: can we include parasitics on the IC package and a combined package to PCB power analysis in hyperlinks?
So it depends. I'll be honest, it depends on the form in which we have the package. If we have the package effectively as a layout, then yes, I can. If I'm taking fairly small off-the-shelf devices, then no. Basically, we imagine the device just has a very high input power impedance. But yeah, if I could get a physical package model, it is possible because effectively it becomes another board at macro scale in the system.
Perfect. Thanks, Steve.
My pleasure.
Excellent. All right. So I forgot to mention earlier, this session has been recorded, so everyone will get a link to the recording in the next few days, as well as copies of the presentations. Obviously, if there's any more questions that come up after that or otherwise, again, don't hesitate to contact us. Thanks again for attending. This is a series of webinars. So we focused on PDN AC analysis today. Previously, we looked at DC analysis. And then before that, we were looking at advanced DDR design and SerDes analysis as well. So if anyone missed any of those, do let us know. Happy to send the link to the recording and or the presentations as well. So again, thanks very much indeed. Thanks for your time, everyone. And with that, I will let you go. Have a good day. Thanks and goodbye.